All right, so I think we're connected apparently, and so let's get going. I changed this up a little bit, after I actually created the announcement. I had something like 13 reasons why simulation modeling, should be a requirement, a lean requirement. But as I was going over the list, I realized, there was some duplication, and in the interest of keeping this more focused, what I did was I eliminated some of those. So I'm not actually eliminating the topics, I'm just eliminating the number of items that are on the list. So I got it down to the David Letterman top 10 list of reasons why model building is a lean requirement. So hope you'll forgive me for that. In terms of my expertise with simulation modeling, let me make it clear, I'm not a simulation expert, but I do have a little bit of experience, maybe more than most. I was actually VP of lean manufacturing, the lean manufacturing process or practice for a company called Quran Consulting Group in San Diego, California. And they were the West Coast representatives for Pro Model Corporation at the time. And their main focus was simulation modeling. And I joined them thinking that, boy, I could really learn a lot here and get good at it. And, a certain amount of it did rub off. But I did realize also that to really get good at it, I was going to have to become kind of a simulation modeling specialist to really be at the top of the game. It couldn't just be a hobby or a side interest if I wanted to be top of the game. So I continued my focus on lean manufacturing, but I did deepen my appreciation for simulation modeling there, and I got to see what real experts in modeling were like and how they thought. And one thing that I'll share with you is that when you start getting into this, your thinking, your process-related thinking becomes deeper, I think, because the kind of questions you need to ask, the kind of probing you need to do to get a model to work correctly and reflect reality needs to be pretty deep. And so you can't get away with just superficial understanding of how a process works. You really have to drill down deep. And so one of the deepest learning experiences for me was seeing people in action and the kind of questions they were asking and the kind of thinking that went behind their questions, so that they could go away and actually build a model that was going to work correctly and model reality and give you good results. Okay, so here's the agenda for our webinar. What is it? So quick definition for those of you that might be new to it. I'm using this acronym just so I don't have to type out all these words all the time, DESM, but just know that stands for Discrete Event Simulation Modeling. 10 good reasons. So they're now down to 10. And then model building options. So if this is something you want to pursue further, I have some options for you at the end for how to get started. So here are the original 13. And I don't have to read this to you, but you'll be able to download this whole presentation if you want to look at it in more detail. But the last three, 11, 12, and 13, are really sort of duplicates. They're included in some of the other ones. So I just, as I said, I just simplified the list. Okay, so here's a definition. I actually asked ChatGPT to give me a definition. And the first definition was accurate, but it was kind of technical, using a lot of specific terms. And so I said, thanks a lot. That's great. Good job, ChatGPT. But give me like a simplified version for a beginner, let's say, of what discrete event simulation modeling is. So it came back with this. So it said, simulation modeling is like a video game. And in this game, certain things or events, so hence the term discrete event, certain things happen that might change the situation. Like you finish the work on a product, or you have to move, or the time, some kind of event happens during that process. Those are the events that the software keeps track of. So in other words, the software doesn't have to keep track of every second of simulation time. If I'm simulating a week of work, it doesn't have to manage every single second, but it manages the events. So it goes to the next event within the model when it's finished with one. So that's an important, thing to understand. So in that way, it can model a lot of time a lot of simulation time in a short amount of elapsed time. So the idea here with model building is to create a model of reality, presumably, and be able to run experiments and try things out in a simulation environment as opposed to doing it in the real world. Now, ultimately, of course, you need to do things in the real world, but if you can reduce the amount of adjustment that needs to happen later on, that's a huge benefit. Because as I've said many times, the absolute worst time to be making a so-called process improvement is when the process is already implemented. It's already running. Ideally, we can find things and improve things in a much cheaper and faster environment than actually having to do it physically. Now, that's not to say that things don't come up in the actual physical world, but the more we can plan, in other words, and anticipate within a simulation modeling environment, the better. So that's the key concept here. Because the most expensive and the most disruptive time is to do it when the line's already running, for example. So this idea that you can have a bad design and then Kaizen it is really not a good approach at all. Okay, so that's it. Now, we've noticed in my 20 plus years of lean coaching and consulting training is that simulation isn't used that much. Now, your company may be the exception, but a lot of companies are not really embracing modeling as a key strategy, as a key tool. They may have bought a copy, of some simulation modeling software, but they're not really embracing it. So why not? Let's kind of review my thoughts on this, and you might have some other ideas as well. If you do, you can please enter those in the chat. But first one is lack of appreciation. So that's why we're here. In other words, lack of knowledge. Don't really know what it's about, and therefore it's not on your radar screen. So we're going to identify the top 10 reasons here in this webinar, so that will help. Second reason is there's a learning curve involved, especially with complex or commercial simulation tools. So you remember, if you've probably heard this, I'm sure Malcolm Gladwell had this concept of the 10,000 hours to gain mastery in any subject like playing the violin or learning how to be a simulation modeling expert. You have to invest 10,000 hours. Now, 10,000 is just a made up number, but the point remains that it requires some effort to learn and practice and get good at it. So simulation modeling has a steeper curve than maybe some other tools that we want to use. Third reason is lack of management sophistication. In other words, upper management, who ultimately makes the decision on business strategies and direction and tools, et cetera, are not as sophisticated as they could be in terms of using what's out there. So even if you have a groundswell of support at the lower levels in a company for things like simulation modeling, you need upper management support to really embrace it as a business strategy, and maybe there's a lack of sophistication there. Again, not pointing fingers at any individual or company. Number 4 is past experience. So maybe it was tried out, but maybe with not enough expertise, without enough sophistication, let's say, and the results were inconclusive or maybe even negative. So we tried this already, it didn't work. Okay. Next one is lean manufacturing bias. So we've run into this occasionally where lean folks, maybe like most of you here watching this, have a tendency, which is not wrong, but have a tendency to think that lean is all about getting your hands dirty and going to the gemba and seeing with your own eyes and engaging with people. All that is correct. But that doesn't mean that we can't be using tools like simulation modeling to help even to help communicate. So just going to the gemba is great, but you may have some additional opportunities here, and the proof is in the pudding. One of the biggest clients of ProModel Corporation, which was shared with me by a ProModel salesperson. ProModel is one of the commercial software packages, simulation modeling packages, is that one of their biggest clients in recent years is Toyota. So don't think that because Toyota is the lean gold standard that they don't use tools like simulation modeling. They do. And the final one is cost. Cost shouldn't be really a huge obstacle for most organizations, but those licenses are not cheap. They can go to 4 figures or even 5 figures for a single license, depending on which one you're looking at and what you're trying to buy. So it's not the kind of thing that we typically would buy as individuals just to play with it. You could, but typically we wouldn't do that because of the cost. So it shouldn't be a showstopper, but that is there as well. It's not, it's justifiably expensive considering how much, how sophisticated these products are, and how relatively small their customer base is going to be. Not everyone in the world. It's not like Microsoft Word, right? Not everyone in the world is going to be using these tools. Now, in terms of getting more familiar, if you want to drill down a little bit deeper in simulation modeling after this webinar, I looked on Amazon just a few days ago, and there's a lot of information available, a lot of books and other things available on simulation modeling, no shortage. So I just mentioned this one by Stuart Robinson because it's the one that I have and the one I've been reading and like. And it's geared towards the practitioner or the user, right? How do you use models? How do you interpret results? That more on that direction rather than how do you technically build a software model. So it's not software oriented, it's more theory oriented. Now on the software side, again, there's a lot of help there, but Python seems to be a language that is strong in simulation modeling. And there's a book that I also have in my library called Modeling and Simulation in Python. So if you want to get more into the coding part of it and have those, either that desire or those skills actually, there's information there as well. So no shortage of help. Okay, so let's do a quick poll here, just to poll how you guys are racking up in terms of your simulation background, just out of curiosity. I'm just going to leave this here. Let's see, publish. I'm going to leave this up. And there are 3 questions. So have you used discrete event simulation modeling yourself personally? And the first answer is no, but I'd like to learn. Second one is yes, but I'm kind of at the beginner stage. And then the third one is yes, fairly extensively. So anyone who's like intermediate, you don't have to think of yourself as an expert, but intermediate to maybe more advanced intermediate or expert level. Okay, so far 27%, or about 1 in 4 is no, but interested in finding out. So you came to the right place for that. Yes, but just getting started, lower on the learning curve. That's most of you. And then about a quarter of you are more experienced with it, probably more than I am. So here we go. I'll just leave this poll open for a little bit, let everyone have a chance to respond. So here are the 10 reasons that I would say that we want to build a case for using modeling in the world of lean manufacturing, process improvement. And I got some help in terms of creating a list, again, from ChatGPT. I said, give me the top 10 list. I asked ChatGPT to give me the top 10 list of reasons. And it did. And I didn't use all of them, but did a decent job, right, in coming up with an initial pass on the reasons. So reason number 1, enables virtual experimentation. So definition is a simulation model allows designers to experiment with different scenarios and parameters without incurring the costs and risks associated with actually physically implementing. That's huge. Now, there is a cost in building a model, right? There's your time. There may be cost of software. There may be cost of getting outside help if you need it to build a model. But that cost is going to be a tiny fraction of the cost of actually doing it physically. So well worth the investment. We always say on a line design project that we work on, let's take a part of our budget, if that's a concern, and allocate it to model building. And it won't happen up front. It'll happen sort of halfway in between the process, the line design process, where we want to test out our proposed designs. But let's make sure we fund that. We have a budget for that. But it's going to be, I don't know, I'll make up a number, 5% or less of the total cost of the project will be the model building part of it. And that cost is going down, by the way, significantly over time. Okay, so the details of this virtual experimentation. The importance of this is as your cost and risk goes up. In other words, if this is a $100 implementation or Kaizen event, you may not need to do it. If it's a $3 or $4 million line design, you may want to seriously consider doing it. And again, including that as part of the budget. Now, the important thing to understand here is that simulation modeling doesn't actually give you the right answer or give you the optimum answer necessarily. Now, there may be tools out there that I don't know about that will move in that direction. I'm not sure. Again, if you have some expertise in that area, let me know. But as far as I can tell right now with my use of it, it's great at running experiments very quickly, but you as the user have to come up with what you want to test for. So you create scenarios. That could be scenarios of change of mix, change of volume, change of the amount of variability that you allow in the system. There are a host of things that you want to test for, but you have to define those scenarios. And then the model can run it very quickly and you can look at the results. And those results typically would be, what was my throughput during that simulation time? How many units did I get through the system? And then you want to look at capacity or utilization, productivity, if you will, of the individual resources in order to look for bottlenecks, look for performance at the individual workstation and individual operator level, and get a deeper understanding of, based on this scenario, here's what you might expect to happen in the physical world. Okay, so experimentation. Next one, bottlenecks. So many of you, I'm sure, are familiar with Goldratt, theory of constraints. So you're never going to get more units out of a system or an assembly line, let's say, than the slowest process. So, and that would be the bottleneck. Now, being a bottleneck in a process isn't necessarily bad if you can meet your customer demand, because there is always going to be some constraint, some bottleneck. But simulation modeling can be extremely useful in identifying where those bottlenecks are. Again, ahead of time, rather than having to observe a physical line running and see where things are piling up. That'd be another way that you want to do it. So the beauty of a simulation model is that it's going to track performance at every resource, and that's at a fairly detailed level. So individual workstations, buffers, people, secondary resources like conveyance devices, AGVs, etc. It's going to track all of that, and you can then look at the output, the results, and identify those that are either over capacity or approaching capacity, so they're the potential bottlenecks in the system. So our rule of thumb when we look at the data, the output data, is that if you have resources that are over 90% utilized continually, you want to take a look at that, because that could be possibly constraining the flow. And you can run experiments, right, and see what happens when you add resources to that particular area of the flow. The other important thing about or benefit of using simulation modeling with bottlenecks is that you don't typically have a bottleneck that you fix. When you change the mix and volume of your sequence, of your production plan, then bottlenecks can actually move, because not every product has the same work content time. And certain mixes of products can drive certain resources differently than other mixes of products. So one of the things you want to look for is this phenomena of shifting bottlenecks. And that's, again, very difficult to actually do in the real world. Because in the real world, imagine you've got to be physically observing the performance of a line with different mixes that don't happen, right? Don't happen all the time. So again, it can be tremendously helpful to isolate those parts of the flow that could be potential constraints to achieving the volume or throughput that you want to achieve. Okay, so there are a variety of tools to fix bottlenecks or help address them. One of them is buffers, or allowing additional pieces in the flow. That's one could be a very powerful technique and not that expensive depending on what you're doing. I mean, there are problems there if you have a huge product to add additional units, but oftentimes that can be a very easy and inexpensive way to improve performance. Another one is sequencing. So typically a company like Toyota or anyone that's doing mixed model manufacturing will have knowledge and document some sequencing rules. So the order in which you want to do the work or run the line will make a big difference in terms of the amount of delay and blockage that you create during the working day. Another great technique, if you can do it, is to eliminate waste. That means typically eliminate time. So can we improve the process and reduce the work content time at the entire line or at a station to reduce that bottleneck? And then finally, you can reduce bottlenecks by adding resources, but that's the kind of the last thing you want to try to evaluate, because when you add resources, you're adding cost, right? You're adding space and you're adding potentially some capital equipment. So it sometimes happens that you have to add resources, but it's not your first choice. You want to exhaust the other opportunities to improve first. Okay, so simulation modeling for bottlenecks. That's great. Now, similar concept, maybe a little bit different, is optimized capacity utilization. So as I mentioned, one of the outputs you're going to get from a simulation model is you're going to be able to look at each individual workstation and, if you wish, each individual operator that you define in that model, and look at how much utilization or capacity they are consuming. And so there are two things you want to be concerned about. One is if a person's overutilized, then that's going to be constraining the performance of your model. The other thing you want to look at is underutilizing. There's a Goldilocks or sweet spot for utilization of people, for example, where you don't want them totally occupied 100% utilization, because that's going to really almost guaranteed going to constrain the throughput of your model. But you don't want utilization of 50% either, where half the time they have no work to do. So this is a great way to allow you to achieve that balance and get into that Goldilocks zone, not too hot, not too cold zone of utilization on your resources. That's why I say optimum capacity is achieving your customer demand or your capacity goals, but without having to over-resource. Because remember this, you can always achieve any capacity you want by adding resources. You just keep adding resources and your throughput's going to keep going up. But the question is, what do you need, right? Versus what are the inputs you need to achieve that? And simulation modeling can be very useful, right, in understanding that. All right, reason number 4. By the way, I'm going to go over to chat. Okay. Oh, on the chat, by the way, let me take a pause here for a minute. Brad, I'm going to mention some tools as well, some free ones. So thank you for that. SimQuick. I'm not familiar with that. I'll take a look at that. Ashok, Richard also provides Excel-based free simulation modeling tool. Okay, I'll talk about that too at the end of the webinar. Okay, reason number 4. Back to work here. Reduces production lead time. Now, one of the things I learned, I've mentioned this in the past, but I was reading an interview with, I think it was Goldratt and Taiichi Ono, right, the father of the Toyota production system, after Taiichi Ono had retired. And he said that, when they were implementing Lean or the Toyota production system at Toyota, they didn't really want to share what they were doing with outsiders. He said he was happy to help other Japanese companies, but kind of out of patriotism, he didn't really want to share what they were doing with Americans or the Europeans or whoever else they might be competing with in the world, because he said, that would just make them harder competitors with us. But when he was interviewed, he'd already retired, and he said, at this point, Toyota is strong enough. I'm not really concerned about that anymore. So he was willing to share some things that he hadn't really shared before. And I'm sure you know this. If you look for a definition of lean manufacturing, or even the Toyota production system, what you'll see oftentimes is a definition that says lean is all about eliminating waste in a system. And actually Six Sigma is about improving quality, right? And then Lean Six Sigma is about both, I guess, combined. But the idea of lean as being primarily focused on eliminating waste, according to Taiichi Ono in this interview, was wrong. He said that was a byproduct. Our first number one focus was reducing lead time throughout the system. I mean, going all the way back to external suppliers and then through all the manufacturing processes, right, to the customer, focusing on shrinking that time down. Now, how do you shrink the time down? Well, elimination of waste has something to do with it, clearly, and also improving quality has something to do with being able to shrink down that time. But that was the primary focus, and still is, and that was what he didn't want to share with the Westerners. So what he did was he sent the Westerners on kind of a not totally incorrect, but pretty much a wild goose chase. Okay, all you Westerners, Toyota is all about eliminating waste. Go eliminate waste, right? Wherever you find it, go eliminate the waste. Whereas internally, we are focused on reducing time, right? Lead time. So that was an interesting insight, I thought. By reducing time, it, number one, requires all these somewhat secondary things like eliminating waste, but also it has an impact on a lot of the characteristics of the company. And maybe it's one of the reasons why Toyota tends to be like sometimes wildly more profitable than their competitors, because of a long-term, decades-long focus on reducing that lead time. Okay, so simulation model can help a lot in terms of analyzing this. Now, the primary technique to, at least within the four walls of a factory, to reduce that lead time is to do whatever you can to link and balance the processes. In other words, eliminate any kind of, as much as possible, handoffs and as much as possible accumulations of product, and get things to be able to move from step to step to step to step without delays and without any defects, right? Any mistakes. That's the primary focus. So the old days, the MRP days, where you would build a subassembly and then you put it back into stock, and then you'd reissue the subassembly on another work order to the next down level process or work order, that is gone away, hopefully, right? Because that just adds a bunch of time, right, to the overall response time to the customer. Within your simulation model, you're going to be able to see the flow. You're going to be able to measure the time, at least in simulation time. You're going to be able to measure that, and then you're going to be also able to see where that time accumulation is, which oftentimes is inventory accumulation as well. See that, and then identify improvement opportunities to reduce or eliminate that. Now, one beauty of embarking on a line design project is that you're starting with a blank sheet of paper, psychologically, and it's an opportunity to eliminate a lot of those handoffs and a lot of that disconnected work from the start, right, at the design level. But if you already have something, a model will actually give you a great way to zero in on where those opportunities lie. Another thing that some companies, some of our clients, as a matter of fact, have embraced as almost like a slogan for manufacturing engineering is short and wide. So when you're designing an assembly line, for example, the emphasis is short and wide. So what does that mean? It means that if you can do work in parallel, then do that, as long as it makes sense. In other words, move work into feeder lines as opposed to putting everything into a long sequential line, because that's going to reduce the time, right, the elapsed time to get through, because you're doing more work in parallel. So manufacturing cycle time, or MCT, will go down if you can do that. So again, a simulation model lets you experiment with building or designing short and wide lines without having to actually do it yet. Okay, number 5, reduces inventory. So, Jeff, 6 Sigma is about reducing variation. Okay, agreed. So, correction, I mean, you will see that it's related to quality on the internet if you search for that, but what you're telling us here is that it's primarily focused on reducing variability, right? Okay, inventory levels. So one thing to understand is there's a direct relationship between MCT that I mentioned earlier, or some people call MCT MCPT, which stands for manufacturing critical path time. So the actual lapse time to get through the system, not the total work content time. Because if you have a lot of work in feeders, the total work content time is going to be greater, but the time it takes to get through is going to be less. So the time to get through the system is directly related to the amount of WIP you're going to require. And that makes sense, right? If something's on the factory floor longer, you're going to have more WIP than if you could get it done more quickly. So from that point of view, then, if you can optimize that time, your WIP inventory specifically is going to go down. Now, there are ways of managing and reducing raw material, finished goods. That's a topic, interesting topic, an important one as well. But certainly a shorter line is going to give you less WIP. The other thing that, in terms of inventory, that a simulation model is going to help a lot with, one of the most common questions in our workshops, our line design workshop, when we talk about buffers, or we call them in-process Kanbans, but buffers between stations, to overcome variation in time. And remember, Brad, time variation in a mixed model line is almost impossible to actually get rid of, because different products have different work content. So when you're mixing them, building different products on the same line, and you're going from one model to another that's different, those time variations are going to be there, like it or not. So that's one of the challenges of mixed model manufacturing, is understanding the sequencing rules and the way to reduce that amount of variation. So an in-process Kanban or a buffer can help overcome some of that if you're following a hard one with an easier one, for example, because the easier one's going to be done sooner. The one downstream is going to take longer. So if that upstream process has to wait until the downstream station frees up, then that's a delay, right? That's being blocked. But if they have a buffer, you can move the unit into the buffer or into the in-process Kanban and start working on the next one upstream. Now, of course, that method's going to run out of gas at some point, right? If every product downstream is going to be longer, then at some point the buffer is not going to help you anymore. So that's where mixing, alternating high work content, low content can be beneficial, right? So I was getting back to the most common question asked, or a common question asked in our workshop is, when do we calculate buffer sizes? And our answer is never, because there's really no formula per se. There are ways of estimating, but when you change the mix of products, then that buffer requirement can change as well. So what we typically say is, if we didn't have simulation modeling, what we would typically say is, hey, put in one. If you know there's variability, put in 1 unit's worth of buffer, and that typically will overcome 1 takt time worth of imbalance just by itself. So one unit can be a big help. But from that point forward, you're going to have to evaluate that, by observing, by going to the Gemba, watching the line perform, and seeing where there might be the need for other buffers, specifically in front of bottleneck kinds of resources. Now, you can speed up this process, this analysis process, with modeling, right? Because you can actually play with buffers, quote unquote, modify buffer sizes, and really optimize the throughput by running experiments with buffers. So that's huge. That's really really helpful. and not have to just fix it later, so to speak. Okay, number 6, improves quality control. Well, this is maybe a slightly weaker one, but when I was thinking about it, yeah, there are some ways that quality could be impacted. For example, if you have rework that takes place that can't be eliminated, at least in the short term, you build those rework loops into your model. And that way you can really kind of assess the impact or maybe the importance of improving that or reducing that rework by being able to assess the impact of that rework or yield even on the performance of your model. That will give you some more data basically to say, hey, before we go too far on this, we really need to fix this issue of rework or yield because it's having a dramatic impact on our model. That could be very useful. If there are other issues, again, typically related to yield or rework, you can actually build those into the model and assess them, and hopefully zero in. I get the idea here would be to zero in on those areas that need attention, that need to be improved before you go live. All right, number 7, enhances flexibility. So this is a big one. In fact, we're currently, it's going slower. It always goes slower than we'd like, but we're working on a book on flexing. So flexing is our term for flexible employees specifically. So the idea here is that you don't have to staff an assembly line or a value stream with a person at every station. You can understaff it, not change the line. You're not doing a line rebalance or a line redesign, but you can understaff it and have people move. And there's some benefits to that. If you have a mixed model line where there are natural imbalances, then some of that variability can be overcome if people can just move and work at another station. Now, we have to have some rules and boundaries around that because those people can't just move anywhere. You don't want chaos and you don't want people working in stations that they don't know. So they have to be cross-trained for one thing, and then you have to have some flexing rules as to when you move and where you would move to. But these are beautiful things that can be modeled as well. And by the way, this will be included in our book, but there's something like 5 or 6 kind of standard flexing strategies, different ways of flexing, all the way from kind of a more conservative flexing approach that we teach called 1 up, 1 down, all the way to things like rabbit chase, and there are a number of them. So these are things that can be modeled. And this can be useful in a number of ways. One, it can demonstrate the value to you of having flexibility built in to your future design. It'll allow you to adjust the throughput or output, if you will, without changing the line. And that's really huge. Currently, a lot of companies, and I think Toyota is included in this as well, will try to run their lines at the same volume every day. So if you design it for 133 units, you try to build 133 units every day. Now, you can do that if you have a nice fat backlog of orders. But if you don't, then what are you going to do? Build the stock? Build to inventory? I don't think so. So the ability to adjust the output of the line, but without having to do a line rebalance where you recalculate takt time and you rebalance the work and you change the number of workstations, all that stuff. If you can do it by simply removing people, that is huge, hugely beneficial, right? If you have that need. So testing this out and proving it in a simulation modeling environment and actually convincing management that this is a good thing to pursue could be extremely useful. The other thing is convincing operators, because if people are used to the my station mentality, where here's where I work and I have my coffee warmer and I have family photos here and this is where I go and this is where I do my work. You need to break that, that goes away if you're having people flex. So understanding how this would work to train them and also understand the benefits can be useful if you can show them a model, right? And actually use that as part of the buy-in process of getting them to do this. But it can be huge, and as a matter of fact, I don't think I have the book on my bookshelf. I'm looking at the bookshelf right above my head here, but basically, people that have implemented this have been saying, Gordon Giron is an author. He has a book available on Amazon. Giron, Ghiran, I think. Ghiran. You can find that. And he rarely has less than a 30% productivity boost by getting people to flex. Now, why is it boost? Because when you allow spaces for people to move, they can overcome the imbalances. So that 30% used to be waiting time or block time, and now it's able to be value-added time. So very important benefit here of simulation modeling is to understand this. Even if you're not doing flexing today, to do experiments and demonstrate the value of this, because this is one of the lower hanging fruits in the whole world of lean improvements is flexing. And it's one of the most least utilized, let's say, least implemented. Okay, number 8, improve resource allocation. So again, this is pretty standard, but one of the outputs of a simulation model is percent working, percent blocked. That's where the unit is finished at a resource, but it can't move forward because downstream, they're blocked from moving it into the next station. So blocked, and then there's waiting. That is, I want to work, but I ain't got nothing to work on, right? So upstream, there's a delay. So that's waiting. And then we have the fourth category, which is idle. And idle is simply, I don't have any work and I don't need any. I got nothing to do, right? So just pure wasted time. So a model will give you that feedback at a very detailed level, every station. And so this is where we can really drill down and understand what our, at least at the model level, what our situation is and what we can do to improve the level of utilization. Again, not to 100%, but to a reasonable range, which typically we set to be between 85 and maybe 95 or less % utilization. If you're below that, then that's an opportunity to improve utilization. If you're above that, then you're running some risk of, when the mix changes, that resource becoming a bottleneck, which you don't really want either. Okay, so tremendously useful there. Reason number 9 is test new concepts. So you might want to try out things that you really wouldn't do you'd have to be hard pressed to try this out in the real world, but in the simulation modeling world, you're willing to give it a try. It could be a very different flow structure, for example, or maybe today here's a good one. Maybe today you're building in small batches. You'll build 100 of a product, then you'll do a line changeover and you'll build another 100. Well, that could be the best solution, but maybe mixing or maybe smaller batches would be better, right? Get better results, better throughput. So how would you know that without modeling it? It would be hard, right, to test it out in the real world. So those are, and by the way, I've run experiments myself with clients where it turned out that batching, not batching in the sense of moving material in batches together, but actually building the same product over and over again, one at a time, right? But over and over again, actually gave us better results than trying to mix too much. Trying to change the model too much. There are a number of reasons for that. One is you actually have less variability if you're running the same product over and over again, from product to product, right? Because it's the same one. And the other thing is there's a learning curve, even with experienced workers, that if you're doing the same one again, you're going to be a little bit more efficient, actually, because you just did it, right? Versus here comes a different model. What do I need to remember? Even if you have work instructions or you got a touch screen in front of you to remind you of the steps, there's still a little bit, lowered productivity, let's say. than doing the same thing over and over again. So these are all things that can be tested for, can be extremely powerful. All right, last reason that I included here, reduces risks. So again, we've touched on this already a little bit, but the idea here is we don't want to have to do Kaizen events to improve the performance of a line after it's implemented, or at least reduce that to a bare minimum. So we want to reduce the risks of not getting what we want. And if you don't have modeling, then you're relying on a static design, right? A static, like an Excel spreadsheet to calculate resources. You can do lots of good calculations, and this is what we do as a first pass, but you won't be able to test it in a dynamic environment, with a mix of products, changing the mix of demand, experimenting with buffer sizes, all those things. You won't be able to do that in a static spreadsheet. So again, worst time to have to make a change is after it's already completed. So we want to avoid that as much as possible. So this is huge. Even if you learn nothing from a simulation model, which I've never seen happen, you always learn something. You always find some way to improve your design if you build a model. I mean, virtually guaranteed. But even if you didn't, it would be worth doing it simply as an insurance policy, right? to reduce the risk of running into that later on. Okay, so I hope we've made a strong case here. We could probably come up with more ideas. Ken adds engaging the operators, yes, and getting the buy-in. So that's important. If you're going from a non-lean environment to a lean environment, and you want people to behave differently, showing them things, like showing them a model, especially if it's animated, can be extremely helpful to get the buy-in. It helps people, picture in their minds. And kind of a humorous thing about animation where you see little people moving and you see products flowing, on the screen. What simulation experts say is you don't really need animation. And if we're up to them, if they were the end user, they wouldn't be using animation. They just look at the data, right? Look at the numbers. But they said animation is important in order to allow management to understand the model. You have to show them the pictures. So most of the commercial packages include animations. Okay, Ken, testimonial there. All right, make improvements to the process. Super. Yeah, I haven't seen any simulation projects where some good didn't come out of it. Now, if you want to get started with this, let me offer a couple levels of options. Lean Design Simulator. So this is something we created with the help of Karan Consulting Group, my former employer. We developed it's kind of a specialized tool focused on assembly lines or on value streams, where you have sequential work, all right, that's flowing. And the goal here was to try to make it simple enough so that people didn't have to go through this learning curve of learning this whole new complicated software package. So the beauty of the Lean Design Simulator is the data model is built in Excel. So you complete a series of Excel worksheets where you define your products, you define your processes. How are the processes connected? What are the work content times? What's your production plan or your sequence? So it's all pretty straightforward to understand. And then the simulation calculations itself, the discrete event calculations, happen in kind of a black box. So you just identify a few things like what's the warm-up time? Warm-up time means if you have an empty model, it's like an empty factory. Right? It's going to take a while for that first unit to get to the end of the line. And if you're starting to collect data from time zero, you're going to get nothing until finally something starts coming out the end of the line, completed product. So the warm-up time is just time you're allowing to fill up the line, basically, before you start collecting data, simulation data. And that warm-up time is going to be related to how long does it take, right, to get to the end of the line. You need to have some feel for that. So that's one of the inputs. And then you actually have the runtime, which would be, in simulation minutes or hours or days, how long do you want it to run? And so the black box will run, the Lean Design Simulator black box, and then you'll get the output. Again, Lean Design Simulator does not give you animation. So don't expect to see little people walking around on the screen or products flowing. We could do that, but that would be like, next generation. On this one, you get an output file that shows you by resource the utilization and shows you the throughput by actual individual product going through that model. So you've got everything you need, really. Once you learn how to read it, you've got everything you need to understand how that model is performing. Another beauty, so other than Excel, you're doing your data entry and your data analysis in tools you already know. But the other beauty is it's included in the Lean Design Studio. So if you're a member of the Lean Design Studio, which does have a cost, the Lean Design Simulator is included as part of that. So again, in red here, meaning minuses, negatives, no animation. It only supports one level of feeders. So if you wanted to model a feeder line, feeding another feeder line, feeding another feeder line, it won't do that. It's limited to one feeder, which in our experience is perfectly adequate most of the time. But if you wanted something more in depth than that, you'd have to use another tool. And then also on flexing, it models flexing, but kind of a Superman style flexing. That means if an operator can work at one of 5 different stations, you define that, and that one of the 5 is open, that operator will just go to that station, within the software. Like Superman, will go instantly go over there. You can add some move time to modify that a little bit, but what you can't do is define this one up, one down kind of logic that we'd like to see. So in most cases, that's perfectly adequate. But if you wanted more sophisticated flexing, you'd have to go to another tool. Now, one of you mentioned, let's see, who is it here? Was it Ashok? Here, SimQuick. Not familiar with that, but I did find something called JamSim. So moving up the food chain here in terms of simulation software. So JamSim, I loaded it. I installed it on my computer. I've played with it. It does have a GUI interface, which is pretty cool. It's open source, so it's free. There's a community of people that support it and work on it. It's intended to be equivalent to a commercial simulation package, but it's free. And there are all kinds of training videos as well. If you go to YouTube as well, there are training videos on YouTube for JamSim, how to use it, how to get started, blah, blah, blah. So my initial impression is, hey, this could be pretty cool. But I haven't spent enough time with it to give it a stamp of approval exactly yet. And the other thing is, I mentioned here, there are probably others, and you've already identified one of them. So there could be quite a few others. But this seemed to be a pretty cool one. It was pretty easy to install. I can't give it a stamp of approval from my own experience. But what I've seen is it looked good. It looked pretty good so far. And if you need the animation, that's included. Now next step up the food chain is commercial simulation software. So there are a lot of companies that are developing simulation software that you can buy. And I just listed a few of them here. There are a lot of them. You can do a Google search. You'll find a big, long list. ProModel, I'm familiar with because my prior company was a ProModel rep for the West Coast. Also, I used to own a copy of Simulate, so I've worked with that a little bit. Simulate started out being like a affordable simulation software, but I think what happened was they realized that, hey, we can't make enough money selling this simulation software cheap because there aren't enough customers, to help pay for it. If it were Microsoft Word, maybe we could, but not at our price. So they've increased their price significantly over time. But still, it's one of the more affordable ones. FlexSim is gotten extremely popular. I believe FlexSim is a 3D animation as well. So some of these very cool models you see, the 3D machines and people, etc. FlexSim will support that. I'm not sure that ProModel does. ProModel used to be just 2D, but I'm not sure where they're at today. And Simulate, I'm pretty sure, is 2D as well. So FlexSim 3D. John Deere, for example, is kind of standardized on FlexSim as the simulation tool they use internally. And then there are a bunch of other ones. Arena. I don't want to disparage any of the companies that I didn't list, but there are so many of them that I just threw out a few that I could remember. You're going to get probably a better support with commercial software than maybe a free software or open source software. I would guess, right? Because that's their business, and you might even get someone to talk to or help you, whereas the other ones not so much. You're going to get more functionality than the LDS. LDS is the Lean Design Studio, the Lean Design Simulator version that I shared earlier. You're going to get multi-level feeders if that's of interest to you, and also they're more general purpose. So assembly line simulation is probably the easiest or straightforward. But if you wanted to model all kinds of other things, probably this commercial software would support those kind of things as well. Like, for example, you may want to model, maybe not you, but someone might want to model a emergency department, where people are entering the emergency department at random. They're not like a production schedule where you've got a nice daily schedule of what you're going to build. They're coming in randomized, and then you have triage, and then you have, they need to be examined by a doctor, and then you may have some lab tests you need to do. Then you may need to find a hospital room for them or discharge them, send them home, etc. Those kind of things that are more like a loop, or a ski area, where the skiers are arriving and this was an actual thing that we modeled in business school. Skiers are arriving at the bottom of the slope to get back on the lift, kind of randomly. They're not all coming in a group or evenly. They're not arriving evenly. They're arriving in bunches. And if you want to model that, this kind of software would probably support that. Now, negative side, high cost. Maybe high is not high, if your companies can afford it, and it's not crazy expensive, but typically $2,000, $3,000, $5,000, $10,000. I think Pro Model for a while there was $20,000 per license. That's kind of what you're looking at. Steeper learning curve for sure, right? To get good at using Pro Model or FlexSim or any of these, it's a significantly greater investment in terms of learning than the Lean Design Simulator that I mentioned the first time. And again, they're not designed specifically for value stream modeling, although they'll certainly do it. There's no doubt about that. But it might be a little more complex to get it to do exactly what you want. Last thing, and this is for the really adventurous for you. I asked ChatGPT, since I've been playing with it, like many of you have too, I'm sure. I asked ChatGPT, hey, can you write me a simulation modeling program to do assembly line modeling? Maybe write it in Python. And there is this library I knew of called SimPy, Simulation Python, right? SimPy library. And of course, ChatGPT said, "Oh yeah, sure, no problem." And I said, "Okay, well, give me the top 10 things you need to know, ChatGPT, that I need to provide to you so you can do a good job of developing this model." And it said, "Okay, 1, 2, 3, 4." It gave me a big long list, and I said, "Whoa, let's just do them one at a time." And it said, "Okay, first thing I need to know is this." And so then I type in something. And then I got tired and I said, "Hey, can I just leave this and come back and we'll keep working on this project later?" "Sure, no problem. We'll store this chat, and whenever you're ready to come back, we'll keep on working on this." So it was kind of cool, right? It's like having a partner to develop a model. So again, I haven't finished that experiment, but interesting. So there's no software licenses, there's no cost, and ChatGPT can even tell you what it needs to know, I'm sure within limits. So totally not tested, but interesting experiment. Now, to be successful in this particular challenge, you better know some Python because it's doing the coding for you, but you've got to run it. You've got to potentially identify bugs. You've got to, there's some expertise required that I don't necessarily have, but we'll give it a try. So good luck with that. And if you have any success with this, let me know. I've actually asked it to if it could do Excel-based, VBA simulation modeling, and of course it said yes again. So, but I haven't pursued this. So all interesting things for the future. Okay, here's some links for you, and then we're done. Lean Design Studio. I've mentioned that a few times. The Lean Design Simulator is in the studio. If you want to check that out, as well as everything else that's there, because it's like a treasure trove of mixed model manufacturing, just go to leandesignstudio.com. And what you'll get to is a login page, but there's a link on there that says find out more. So if you click on find out more, it'll take you to the information page. It'll describe, what's in the studio, basically. JamSim, they've got a website, and it's actually pretty cool. Shows you, what training materials are available, lets you download JamSim for your particular operating system. I think it supports Mac and, Mac, PC, and Android. So jamsim.com. And then there's another third one. If you're getting into Python or using Python, if you're one of the few, there's a pretty cool website group. I guess it's like a user group called realpython.com. They have all kinds of stuff on there to learn Python, as well as advanced techniques. But if you want to learn it, there are tutorials and all kinds of ways of getting started. Okay, last thing, there's my personal email address, rron@leonardogroupamericas.com. Shoot me a message if you'd like to chat some more. All right, so with that, I did pretty well on time. It's 11:04, so thank you for sticking with it, and we'll try to do another one of these here in the near future. So thank you so much for sticking with it. Okay, and we'll talk soon. Bye now.